So, dear examination jury, dear promoters, friends, family, and colleagues, welcome to my thesis presentation titled Role of Sorbic Acid in the Fungal Stability of Water in Oil Emulsions. First, I'd like to give you a brief introduction, but we're going to go a bit backwards. I would like to tell you what are emulsions. Now, Young and Lai have defined emulsions as two-phase systems of immiscible liquids with limited stability. In this aspect, we can differentiate two types of emulsions. The first are oil and water, where the water is the continuous phase and the oil is an isolated, the oil droplets are isolated. An example of this in the food industry would be mayonnaise or sauces. And the second would be water in oil emulsions, where the oil phase is the continuous phase and the water droplets are isolated inside. An example of this in the food industry would be butter or margarine. Other than the aqueous and the lipid phase, or the water and the oil phase, there are other things that are usually present in emulsions. For example, salt, organic acid preservatives, which help keep microbial stability, and also emulsifiers, which prevent the emulsion from separating. Lastly, how do we get from these immiscible liquids to a stable emulsion? There are two main processes: emulsification, which is the use of mechanical force to get to a stable emulsion. And second, it's the process of crystallization, where we get from liquid oil to a solid emulsion. So what are the factors influencing growth of microorganisms inside these kind of products? Well, the first factor is pH. Now, in literature, it is stated that the pH is usually set between 3.5 and 6.5. However, in practice, this pH is usually acidic, so around 4.5. Then the second factor is the structure of the emulsion. So either it is fat continuous or water continuous. If it is water continuous, there is more probability to be spoiled. Preservatives. So two main preservatives, organic acid preservatives, are added in emulsions. One is sorbic acid and the other one is benzoic acid. Now, sorbic acid is usually added in products like margarine and butter, so water and oil emulsions. If the fat content is higher than 60%, you will add less sorbic acid. If the fat content is less than 60%, you would add more sorbic acid. Benzoic acid is only added to oil and water emulsions, so products like mayonnaise or sauces. These three were intrinsic factors. There is an important extrinsic factor also to take into account, and that is temperature. So we have usually, and our experiments are done in this manner, we have refrigeration temperature and room temperature. Refrigeration temperature helps keep the product stable for longer. So what are the microorganisms that can grow inside a water in oil or an oil-water emulsion? Both pathogenic bacteria and spoilage bacteria, but for us, most interesting are yeasts and molds, or commonly called fungi. How does food structure influence microbial growth? This is a matrix of oil. You will see that there is a grid. For me, this represents a crystalline structure. In this oil, let's say matrix, big matrix, there are 10 to the power of 7 to 10 to the power of 12 droplets per milliliter. And as you can see, they're different, so they have varying diameters. In these droplets, the contamination is actually rather small. So there is only around 100 microorganisms per milliliter of emulsion. Now, the growth of these microorganisms is limited by space and nutrients. So they will stay confined in one droplet. And lastly, how food structure influences microbial growth is that it influences the redistribution of organic acid preservatives. If you dissolve a preservative inside your water phase, it will want to redistribute inside the oil phase. This picture is a confocal scanning laser microscopy image of recombined butter. And it's important. Why? The black things, the black little circles here, they are the aqueous phase. The green little dots, they are GFP, or green fluorescent protein tagged Candida guilliermondii. Candida guilliermondii is a yeast. The big blue matrix, it is Nile red stained lipid phase. What does this picture tell us? That microorganisms reside only in the aqueous phase. This is a very important point because all of our later calculations will be done exclusively on the water phase. A second important point that is important to emphasize is that most droplets are sterile. So if you can see here, there is a lot of these black droplets, but only several of them contain actually microorganisms. A little bit about sorbic acid. So the solubility of sorbic acid in its acid form in water is very low. That's why people usually use it in its most common potassium salt form. So you see the solubility is far higher, 582 grams per liter compared to 0.16 grams per liter. In most foods, it is effective in the range of 0.02 to 0.3%, or if converted to grams per liter, 0.2 to 3 grams per liter. The range of effectiveness, not the range, but it can inhibit many microorganisms, including bacteria, yeasts, and molds. Now, the food microbiologists here will recognize food pathogens and main food spoilage microorganisms. For yeast, I underlined Candida because we're using it in our, because I was using it in my thesis. And for molds, I underlined Aspergillus, Cladosporium, and Penicillium species. We also used it in our thesis. How does sorbic acid behave in biphasic foods? Well, first, what are biphasic foods? Biphasic foods are made out of the oil phase and out of the aqueous phase. So I said, first we will dissolve potassium sorbate. And in the aqueous phase, it will dissociate to the dissociated part of the molecule and also to the undissociated part of the molecule. The undissociated or the protonated molecule, this is one and the same thing, and I will be exchanging these terms throughout the presentation. This behavior is governed by something called a dissociation constant, or acid dissociation constant. However, what also happens after the dissociation happened is that the protonated or the undissociated form also partitions inside the oil phase. This is governed by a factor called the partition coefficient. Because it is only the protonated or the undissociated form that exhibits antimicrobial activity, this is for now, for us, unfortunately, a loss of the preservative. A little bit about the protonation dependence of sorbic acid on pH and also about the partition coefficient of sorbic acid. You can see here, so the upper row is pH, the lower row is protonated sorbic acid. As the pH grows, so does the protonated sorbic acid decrease. So at pH 3.5, which is a low pH, we will have around 95% of protonated acid. A very important value to note here is the pKa value. So the pKa value is the pH value where 50% of the acid is protonated and 50% of the acid is deprotonated. For sorbic acid, this happens at pH 4.75. What about the partition coefficient? So this is a table with literature statements on the partition coefficient. As you can see, it varies from 3 to 4.5. So there are different statements what is the partition coefficient. In our study, we chose a value of 3.3 because we found it in important publications regarding emulsion stability. We were looking if there is already some information on the behavior of sorbic acid in biphasic foods, and we found an equation from Wilson and colleagues from England. This is the equation, and it tells that the inhibitory form, so the protonated aqueous sorbic acid in equilibrium, is dependent on the total sorbic acid that you add in the system, on the partition coefficient, which is a quotient of the concentration of sorbic acid in oil divided by the concentration of sorbic acid in the aqueous phase, and also the phi, the ratio of oil compared to the entire volume of the emulsion. So our question was, is this actually how sorbic acid or potassium sorbate behaves when added to a biphasic system? And with this, we come to our main problems and goals. The first one, regarding sorbic acid, how does it actually behave in sorbic systems, in biphasic systems? And we wanted to prove this by developing and experimentally validating distribution model where solid fat is included. The second question was, what about the microbial stability? So what is the effect of this sorbic acid behavior on microorganisms? How would we do that? We would inoculate model water in oil systems and follow the effect of sorbic acid on fungal growth. Then the third question was, which other factors might play a role? So we investigated DSD, droplet size distribution, and temperature effect. And lastly, the holy grail of all applied sciences, can the industry use this? So we wanted to apply it in real emulsions. With this, I come to my first experimental chapter, so model development and validation. How did we start developing our model? First, we had a mole. We established a mole balance. A mole balance it describes the moles of reactants and products in a chemical equation. Basically, it tells you what happens with a substance once you add it in a system. The development then went when we introduced the mass fraction of lipid phase, which is the quotient of the mass of the lipid phase divided by the total mass, and solid fat content, which can be measured by NMR, nuclear magnetic resonance. After several iterations of the equation, we come to the final form. So the final form says that the inhibitory, protonated, or undissociated sorbic acid depends on the total moles of sorbic acid in the system, on the mass of the system, on the partition coefficient, on the mass fraction of the lipid phase, solid fat content, pH, pKa, and also the densities of both the lipid and the aqueous phase. How did we prove this experimentally? So we made model water in oil systems. We used for the aqueous phase a buffer with 1000 milligrams per kilogram of sorbic acid. The buffer was phosphate buffer. For the lipid phase, we used oil, sunflower oil, and or palm stearin. The palm stearin is a representation of solid fat. In order to investigate the dependence of sorbic acid partitioning on the pH, we set our pH of the buffers from 3.5 to 6.5. Later, in order to test for the dependency of sorbic acid distribution on the mass fraction of lipid phase, we also had the aqueous phase set at pH 3.5 to 6.5, but we added either 20, 40, 60, or 80% oil on top of that. And lastly, to check what is the influence of solid fat on sorbic acid distribution, we had a 50-50 system, so 50% of aqueous phase, 50% of lipid phase, and inside the lipid phase there was 35, 70, or 100% fat. We then sampled the aqueous phase of all of the systems and ran an HPLC analysis. HPLC means high performance liquid chromatography. And the idea was to check how close is the sorbic acid inhibitory concentration from the model systems to what we have obtained from the equation. And these are our model predictions. So what does the model predict? What is the behavior of sorbic acid when pH is the variable? On the x-axis, it is the pH. On the y-axis, there are different forms of sorbic acid. At pH 3.5, where most of the acid is protonated or undissociated, most of the acid is in the oil phase. Why? Because it is able to partition. As pH increases, so do the concentrations of the protonated form decrease. Why? Well, because the concentration of the dissociated form increases. Second, these are model predictions of sorbic acid versus the mass fraction of the lipid phase. So on the x-axis, it is the mass fraction of the lipid phase, which ranges from 0.1 to 0.9. 0.1 means 10% of oil in the system, or lipid phase. 0.9 means 90% of lipid phase in the system. Now the phenomenon that we're looking is best illustrated at pH 3.5, where most of the acid is protonated. When there is little oil, there is a lot of sorbic acid present in the aqueous phase. The more oil there is, or the more lipid phase there is, the less sorbic acid is present in the system. Why does this happen? Well, the sorbic acid partitions back in the oil. What happens with higher pHs? Well, not much. Why? Because at those pHs, most of this acid is actually present in its dissociated form, so it will not partition. And what about sorbic acid distribution dependency on solid fat content? On the x-axis, we see solid fat content, or F tot, ranging from 0 to 1. 0 meaning no solid fat, and 1 meaning that everything is solid fat of the lipid phase. And on the y-axis is the inhibitory form, so the undissociated aqueous sorbic acid. Again, we see, best illustrated with pH 3.5, the higher the solid fat content, the more aqueous sorbic acid there is. Why? Well, in our model predictions, we assumed that the solid fat is inert, which means it would not allow for absorption of solutes inside the lipid phase. And now some proof. So this is sorbic acid distribution dependency on pH. This is something called an expected versus measured graph. So the expected values are values that come from the model, so theoretical values, while the measured values are the values that come from the HPLC measurements, so the experimental values. The dashed line there, it is the ideal case scenario. It means that the experimental values are the same as the expected values. Now, you see that the points, the experimental points, they are well placed around this line, which means that our model is in very good accordance with what was predicted. Also, this means that sorbic acid distribution can be well explained by change in pH. Now, for the sorbic acid distribution dependency on the mass fraction of lipid phase, again, we have an expected versus measured graph. Again, we have a dashed line, which is the ideal case scenario. And our black dots are dots at pH 3.5 with different fractions of lipid phase. The blue dots are the data points at pH 4.5. The yellow dots are data points at 5.5. And the turquoise points are data points at pH 6.5. You see again that the points fit around the equivalence line. And we can also conclude that sorbic acid distribution can be well explained by the change of mass fraction of lipid phase. And lastly, what happened with our solid fat? So 0.35 PS, PS polystyrene, means that in the lipid phase there was 35% of solid fat. 0.7 means that there was 70, and 1 means that all of it was polystyrene. You can see that the higher the solid fat content, the more the values, the experimental values, differentiate from the expected line. This is best seen with low pH values. Now, secondly, we wanted to see what was the effect of these observations on the microbiological quality of products. So our problem statement was, how do liquid oil and solid fat influence the antimicrobial effectiveness of sorbic acid? So this is sorbic acid. This is an image of Candida guilliermondii, and of course my little skeleton, the antimicrobial effectiveness. Why did we choose this microorganism as a model spoilage yeast? Well, because it was isolated from butter, from olive oil, from yogurt, and from cheese. How did we do this? How did we perform our experiments? Well, first we had the microbiological experiments, where we inoculated 10 to the power of 2 colony-forming units per gram of Candida guilliermondii in 2 sets of tubes. In these tubes, there was microbiological growth media, then microbiological growth media topped off with oil, and then microbiological growth media topped with a mixture of oil and solid fat. The second set of tubes was spiked, or sorbic acid was added inside it. We placed these tubes for 3 days at 22 degrees and 1 month at 7 degrees and sampled regularly. The samples were then plated, and the plates were kept for 5 days at 30 degrees. The results were read and then plotted in DMFit. And with that, we got our generation times and log phase durations. Now the generation time tells you how fast does your microorganism duplicate. And the log phase tells you how long is the duration until this happens, until this starts happening. And second, we did some HPLC measurements. So we took the tubes that had sorbic acid inside, and we sampled and we placed them at 22 degrees for 168 hours, which is 7 days, or at 7 degrees for 1 month. And we sampled them regularly as well for sorbic acid. And of course, we performed an HPLC analysis on this. Now our results. So there are many more results, but the phenomenon can be very well seen at pH 4.5. So the graph on the left and the graph on the right are the same. They both show growth of microorganisms dependent on the time. This is at 22 degrees, and this is at 7 degrees. You see this is 1 month, and this is around 80 hours. I will also explain what the curves are. So the full lines always represent system without sorbic acid, and the dashed lines represent systems with sorbic acid. The blue lines are are only microbiological media. The green lines were microbiological media covered with oil, and the black lines were microbiological media covered with a mixture of oil and fat. The yellow line is a cutoff value or a spoilage value, which was chosen to be at 10 to the power of 6. Now, what can we see at 22 degrees? That sorbic acid, see this flat line, so sorbic acid completely inhibited growth in the test tubes with microbiological media. And if you see the other 2 dashed lines, so the green one is with oil, and the black one is with oil and fat. So you can see that the log phase is prolonged in the one with the fat when compared to the one with oil. Why is this? Because the sorbic acid partitioned in the oil, so there was less of it to inhibit the microorganisms. Interestingly, at 7 degrees, not only was growth inhibited in microbiological media, but also in the systems where fat was added. So again, the solid fat hindered the partitioning of sorbic acid. And now for HPLC results. So on the x-axis we have time, and on the y-axis we have sorbic acid concentrations. The flat lines, the full lines, are systems with oil, and the dashed lines are systems with oil and solid fat. So this partitioning phenomenon is very well illustrated here at 22 and at 7 degrees. As you can see, it's time dependent as well. And of course, it happened the fastest, so the least sorbic acid was present in the aqueous phase at pH 4.5. Why? Because there was most protonated acid available to partition. In the systems at pH 4.5 with oil and fat, this partitioning phenomenon occurred more slowly. At higher pHs, the phenomenon is not so pronounced. Why? Because most of the acid is already present in its dissociated form. Next, we wanted to investigate other factors. So the influence of temperature and DSD on Candida guilliermondii growth in recombined butter. Why did we want to do this? Because consumers demand food products with less preservatives. How? We wanted to understand which other intrinsic and extrinsic parameters could influence fungal growth. So we chose to investigate the influence of water droplet size distribution, or DSD, and temperature. How did we do this? First, we made our recombined butter. We used anhydrous milk fat in two fat percentages, 82 and 61%. We added some PGPR, which is an emulsifier, polyglycerol polyricinolat, to stabilize the emulsion, and then the rest was distilled water. We then added or inoculated Candida guilliermondii at the level of 10 to the power of 2 colony-forming units, which is actually the level of industrial post-contamination, and you have seen it already in the previous chapters. And we have emulsified at 10,000 rotations per minute for 3 minutes. Then, to crystallize, we used the Kenwood cooking chef for 3 minutes. And then we placed our butter for 21 days at 7 and 22 degrees and sampled for microbiological growth, but also for changes in DSD, water droplet size distribution, and D43, volume weighted mean diameter, which is the average diameter of the droplets inside the emulsion. The last two were investigated using nuclear magnetic resonance, or NMR. So these are some of our results. The D43, again I repeat, volume weighted mean diameter, or mean diameter inside the emulsion. This is the left graph, so you can see here the progression during days, and here is the D43. And on the right is the growth of microorganisms, so the log of colony forming units, progression during days. The points with the circle are points at 22 degrees, so these guys here, or these guys here. And the points with the cross, they're at 7 degrees. So these ones here, and these ones here. Also, blue is 82% or full fat butter, and 61% is 3/4 fat butter. 3/4, yeah, exactly. So, what we can see here on the left graph at 22 degrees, that the D43, so the mean diameter, increases during time. And this is most pronounced at 61, so at 3/4 fat butter at 22 degrees at high temperature. Also, we see on the right side that fast growth occurred in 61% butter, so in the same here. At 7 degrees, we see that the line is more or less stable, so temperature helps keep product stability. The log colony forming units stayed stable in 82% butter, in full fat butter, but growth, and you can see these yellow axes, still occurred in the 3/4 fat butter, so the one that had less fat and more water. Lastly, we wanted to perform an industrial validation. Again, does our model work in the industry? How did we do this? First, we wanted to know which sorbic acid concentrations will inhibit emulsion spoiling molds. These are the 3 molds that we chose because they were isolated from spoiled products. It's Aspergillus niger, Cladosporium ramutanellum, and Penicillium commune. Second, we wanted to know, can the model be used to calculate inhibitory sorbic acid concentrations that will be applied in real food, water, and oil emulsions? How did we experimentally determine the minimum inhibitory concentration, or in the jargon known as mix? So first we used the semi-solid media. Why a semi-solid media? Because we wanted to mimic the structure of the emulsion. We buffered this media at pH 3.5, 4.5, and 5.5. Then we added some sorbic acid inside it in the range of 0 to 2,000 milligrams per kilogram. Then we inoculated with 500 spores of either of the molds and placed this in a 96 multi-well plate in a volume of 200 microliters per well. We then read these plates for optical density changes for 30 days at 7 degrees and for 7 days at 22 degrees. What about the validation in real food emulsions? How did we do that? Well, first we had to discover what were the inhibitory or minimum inhibitory concentrations inside the semi-solid media. And then we had to recalculate these concentrations to be applied to the water in oil emulsions. How did we do that? Well, we used our model and we took into account the final pH of the emulsion, the mass fraction of the lipid phase, or the R, and the solid fat content. We then made our emulsions. We placed them, they were buffered at pH 3.5 and 4.5. We used two fat percentages. So 0.4 means 40% of the emulsion was fat, 0.7 means 70% of the emulsion was fat. We also used 3 levels of sorbic acid. We will see which ones later. And then we inoculated them by using 3-spot inoculation. And there was 100 spores per 20 microliters. 1 spot was 20 microliters. We then placed those inoculated emulsions at 7 and at 22 degrees and visually followed growth for 6 months. So our mix results. Now, these are results for Aspergillus niger at 7 and 22, Cladosporium ramotenellum 7 and 22, and Penicillium commune at 7 and 22. And these are the inhibitory total aqueous sorbic concentrations, so everything that we have added inside the media. It was interesting to see that Aspergillus niger didn't grow at all at 7 degrees, regardless of sorbic acid. At 22 degrees, we noticed that as pH grows, so does the necessary total sorbic acid concentration grows, the one that will inhibit the microorganisms. We noticed this also for Cladosporium ramotenellum and Penicillium commune. However, with Penicillium, we also noticed that at pH 5.5, we noticed growth even with 2,000 milligrams per kilogram, which is the highest allowed concentration by law. We needed to then recalculate those concentrations to the inhibitory form. So from the total to the inhibitory. Because we were making emulsions at pH 3.5 and 4.5, we decided to apply the minimum inhibitory concentrations that have proved inhibitory for all the molds. So the biggest concentration that was used and that was shown as inhibitory, we used it. This is for 3.5 and this is for 4.5. And what about the industrial validation? So we placed our butter at our fat spreads at 7 degrees for 182 days. I will explain a bit this table so that it's easier to follow. First, we need to see here that these are all of the fat spreads with 40% fat. The other ones have 70% fat. We said that we were making emulsions at pH 3.5 and 4.5. This doesn't correspond. Why? Because it is very difficult to completely predict the exact pH. You can only measure it after making the product. So this is the final pH, this is the measured pH, and all of the calculations were made on this pH. And lastly, the 3 sorbic acid levels. So the first sorbic acid level is 0, so no sorbic acid was added. Then we chose an intermediate level, and the third level that we chose was corresponding to the mix elucidated inside the semi-solid media. This is the same thing, the same approach we followed for 70% butter. So after 182 days at 7 degrees, what did we see? First, we saw that sorbic acid, both concentrations, inhibited growth of all the microorganisms. So no microorganisms were there. And were growing. And from those who were not preserved, so from those who had 0 milligrams per kilogram of sorbic acid, Aspergillus niger again didn't grow at 7 degrees. You remember that it didn't grow at 7 degrees inside the semi-solid media. Both Cladosporium and Penicillium grew at both pHs at 40% butter, fat spread. And Cladosporium was growing at pH 4.4 in 70% fat spreads. What happened at 22 degrees? again, you see the same code. So 2 fat levels, 2 pHs, and 3 sorbic acid levels. Now we saw growth in 40% butter, so 40% fat spread, so low fat spread of all 3 molds. Again, no growth in all of the systems with sorbic acid. And at 70%, we saw growth of Cladosporium in both pHs and of Aspergillus niger at pH 4.4. And with this, I come to the general conclusion of the chapters that we were talking about. So first, does the distribution model work? Yes, it does. And it tells us that sorbic acid distribution, or the aqueous sorbic acid concentrations, are dependent on the pH, on the mass fraction of lipid phase, and on the solid fat content. However, when solid fat content is high, the measured values differ slightly from the predictions. What is the antimicrobial effect of this knowledge that we obtained? So first, the lower the pH, the more sorbic acid there is to partition inside the lipid phase. In these conditions, most sorbic acid will partition to the liquid oil. But if there is solid fat present, the solid fat will help retain sorbic acid in the aqueous phase, increasing its antimicrobial effect. How about the other factors that we investigated? Well, the high volume-weighted mean diameter and the high temperature allowed for faster growth. In turn, this means that narrow initial droplet size distribution and lower volume-weighted mean diameter help increase product stability. And lastly, what did we see from our industrial validation? Well, first, that using semi-solid media is good for MIC determinations. And second, that all of the MIC values applied in water and oil emulsions inhibited growth. And we concluded that our model can be used to calculate protonated sorbic acid concentrations during product formulations. Now, this study is an important step in elucidating the factors that govern the fungal stability of water in oil emulsions. But all research never ends. So, which are some things that we would recommend to be done in the future? First, you saw that we said that the solid fat content influences sorbic acid distribution, and that the values that we predicted differ slightly from, the values that we measured differ slightly from what we predicted. How we can solve that? We were thinking that the Kp could be changing when solid fat is present. So maybe a solution is to include the varying Kp in the model. A second information to find out later on, we need to again investigate if molds grow throughout the matrix, throughout the fat matrix. So the theory is that usually the growth is contained inside the water droplet. We want to know if the molds are able to spread their hyphae from out the water droplet. Third, we want to determine if microbial proliferation causes droplet coalescence. If I'm a microorganism, I fill up an entire droplet. To search for further nutrients, do I go to another droplet or not? And lastly, a small practical recommendation. We would like for processors to include NMR and pH measurements routinely during product formulation and processing. I would like to thank Gent University, Van de Moorteller for all their help and support, Corman for the initial experiments with recombined butter, and the Faculty of Bioscience Engineering for allowing me to do my research. So thank you, bedankt, merci, hvala.